Hello, I'm Jinshu from Virginia Tech. Today I'm going to talk about our work on tier memory system. This joint work with my colleagues Hamid, Hanchen, and my advisor, Professor Huaicheng. The increasing memory capacity demands from data-intensive applications is beyond the current server can provide. The additional memory, which is either connected with the emerging technologies like CSL, can expand memory capacity within the server. However, the memory access density on those remote memory is 2 or 3 times higher than DRAM and local. The local DRAM can be called fast tier, and remote one can be called as slow tier memory. The system with both of them to handle the memory access with both high and low latency is really called as tier memory system. The memory allocation policy for the traditional memory tiering is usually first touch. It tries to allocate data on fast tier as much as possible, and then allocate the rest of data to a fast tier, to a slow tier. The basic idea behind memory tiering is quite straightforward. The pages that are accessed more often are assumed to cost more per slow down if they sit in slow memory. So most tiering systems try to keep hot data in the fast tier and push the cold data down to the slow tier. And page migration just about promoting the hot data to fast tier and demoting the cold data to slow memory. It's already for many years that most tiering systems are designing, optimizing, and building their systems based on the same assumption. It is the high-frequency memory access on slow memory tends to give high performance slowdown. But is assumption always true? This is one of the key questions we aim to address. Is how the data always performance critical? Now let's consider if frequent memory access does not always lead to corresponding high performance slowdown. Then traditional page migration policies can actually become a problem. In those cases, the system may migrate hot, but not the actual performance critical pages to fast memory. Also, most memory tiering systems still rely on first touch allocation, but this policy overlooks actual performance contribution from different kinds of memory objects. All of those issues highlight the need for new memory tiering designs. So our goal here is mainly to answer these 3 research questions. The first one is, why cannot hotness represent performance slowdown? And second is, which metric should we use for better getting tiering? In the end, how to apply the new metric in memory allocation and page migration. In this work, we propose a set of new memory allocation and migration policies that go beyond the traditional metrics like hotness. At the core of policy is a new metric that we call it as AOL, the amortized offcore latency. AOL allows for more accurate performance prediction by quantifying the true impact of memory access on the performance slowdown. And we use AOL to get both memory allocation and migration. For the allocation, we perform offline analysis to identify performance critical objects and place them on the fast tier. By ranking the objects based on their contribution to performance, we are able to get near optimal results. AOL can also detect the time periods when the pages are accessed frequently but not giving a high slowdown. So we can apply AOL on the existing tiering systems to regulate page migration to achieve a better performance. To give a sample why hotness is not always a reliable metric, we designed simple benchmark. It has 2 threads. One is point tracing and the other one is sequential rate. The plot shows heat map during its runtime. And we can see that sequential rate is much altered, which has around 30 times more access than pointer tracing. And we can use this benchmark to study the performance of different tiering designs. And the right plot shows a normalized performance relative to DRAM-only setup, and showing the y-axis. The interesting finding is placing the hot data that is the sequential rate data in the fast tier actually gives worse performance than placing the cold data in fast memory. In other words, the cold data benefits more from fast tier in this case. The purple bars show the performance of the state-of-the-art tiering system based on the hotness, and they perform worse than the case when there's no tiering at all. Why? Because the system promotes hot data to fast tier, and any page migration only makes the performance worse. It indicates that hotness or access frequency is not enough for getting memory tiering. To model memory tiering performance, we first use LC stalls, which means the stall cycles causing caused by L3 misses. How about using L3 stall cycles to replace L3 misses? We would like to correlate the metric with performance slowdown. Let's see the plot. The x-axis, the normalized L3 stall cycles. They are measured when the workloads are only run in the first tier. The y-axis is the slowdown, which is time spent on remote divided by the time spent on local. And each data point represents one workload. In total, there are 56. As we can see, the points on the left side show a strong positive relationship. It shows that some workloads can be modeled by L3 stalls. However, not all workloads follow the same trend. We do see some outliers. There are the cases where the workloads experience with high L3 stall cycles, but do not actually suffer much performance slowdown. What is the other factor that we are missing? In the CPU pipeline, the memory operations are sometimes executed in parallel. We can call it as memory level parallelism, or MLP. The overlapping effect of those parallel memory access can mask latency dependency. This is the reason why we see the outliers do not give high slowdown, even though they are experienced with high L3 stall cycles. And we can define AOL as the latency divided by MLP. After applying AOL to stall cycles, we can see all the workloads, including the outliers, can fall into a strong positive relationship. Why and how can it work? Here we define as a slowdown and use P to represent the normalized L3 stalls. The slope K is S divided by P. If our theory is correct, the slope K should depend on a metric that reflects the MLP behavior. We name it as AOL. AOL gives how the increased L3 stall cycles on the remote memory are amortized by MLP. The plot gives how this plot shows the relationship between K and AOL. As you can see, we can fit the data veil with a hyperbolic curve, the blue line here. And we can use the relationship between K and AOL to build a model. So AOL can be used to predict the tier memory performance with very high accuracy. For the workloads with low AOL, they are experienced with high MLP behavior. That's the reason why there are the outliers in the left plot. It means that their performance slowdown is amortized by high MLP. Well, for those with high AOL, they are not experienced with this MLP impact. Later, we can leverage this for further memory allocation and page migration. So first, I will talk about the static allocation by using AOL. First, such allocates the data based on when it's first accessed at runtime. The problem is it does not consider how much different objects usually contribute to performance slowdown. So we propose SOAR, a new allocation policy that places objects based on their performance contribution. It assigns a performance predictor to each object during each time period. It also uses AOL to determine when the MLP impact is effective, and then we can use AOL to adjust the slowdown attribution for these objects. This ranks objects by the attribute score and decides whether to place them in fast or slow tier. To distinguish which objects are more performance critical, it's necessary to do offline analysis. That starts with checking the object allocation, basically when each object is allocated and when it's deallocated. Next, we check the memory access using tools like PBS. This gives us the flow of memory access, including when and where each memory access occurs. In parallel, we monitor system performance by using CPU counters. Then we can have a time series data of predict performance. Now that we have three data flows, the object flow, memory access flow, and predict performance flow. The key question is, for each time period, how do we attribute the predict performance slowdown to each object using their access counts and AOL? We already have the relationship between AOL and its impact on the performance slowdown. So we can use AOL as an indicator for each time period. Each AOL is above a certain threshold. We assume MLP has no effect on the slowdown. In those cases, as the green area shows in this plot, we can evenly attribute the predict performance across objects in proportion to their memory access counts. However, when AOL falls below the threshold, MLP is likely affecting the slowdown. And in those time periods, things get more complex. Multiple objects can be in access concurrently, and they have different behavior. To handle this, we look at the access probability of each object. If an object is rarely accessed, it's more likely these access are impactful. So we attribute more performance slowdown to it. On the other hand, the frequently accessed objects are likely having the overlapping memory access, so we send them with a lower performance score. Then the objects can be ranked based on the attribute score, and then the top ranking objects will be placed on the fast tier, and the rest of them will be on the slow tier. I've talked about memory allocation policy to place performance-critical objects to the fast memory. It needs to do offline profiling to make the decision. In contrast, the page migration is an online approach for migrating data without the offline knowledge. The traditional page migration may migrate hot but not performance-critical pages to fast memory. It will result in no performance gain or even performance drop. In worst case, those ineffective page migration will cause extra overhead. So we can use AOL to detect when those behavior happens during the time periods to further reduce the unnecessary page migration. I'll describe how it works. So first, we use two AOL thresholds to assist page promotion regulation, which can be provided offline. For each time period, if AOL is higher than high threshold, it means that there is no MLP impact. So we can enable all page promotion. If AOL is low enough, it means that there is an extreme high MLP impact on the slowdown. The page promotion should be disabled. If the value is in the middle, we do partial page promotion. The scale of page promotion is a function of AOL, and degree of the regulation intensity is increased as AOL goes lower. Specifically, if AOL is high, such as 90 cycles, the less pages are regulated. In this case, 75% pages are promoted. If AOL is low, such as 60 cycles, the last page should be promoted. In this case, 25% pages are promoted. Let's talk about the evaluation. We have evaluated those different workloads on remote NUMA and CSL and compared with 4 state-of-the-art during designs, including Linux NUMA balancing, TDP, Nomad, and Clyde. Let's have a look how SOAR compares with the other tiering systems. So here we use BCORAN graph workload as an example and compare with the other tiering systems. The x-axis shows the slow tier ratio, that is, how much of total memory is on the slow tier. The y-axis is a performance slowdown. The higher means the worst performance. The green line gives a slowdown for no tier under different slow tier ratios. And the 3 new lines here are for Nomad, Clyde, and NVT. As we can see, under different memory configurations, memory tiering is similar to or even worse than no tier. One of the reasons is that first touch allocation leads to inefficient initial placement of data, which cannot be corrected by later migration effectively. In contrast, SOAR identifies and places the performance-critical objects directly into the fast tier from the start, leading to much better performance. Specifically, it gives less than 20% slowdown under 90% slow tier memory ratio. How about ALTO's performance? In this plot, we show BCORAN. The y-axis gives the performance slowdown. The bar of CSL here represents the performance on CSL-only setup, which is roughly 78% slower than the local tier. The bar of no tier shows the performance under the first touch only policy. For the state of tiering systems like TVP, NBT, Nomad, and Clyde, they deliver worse performance than no tier. As you can see, after integrating ALTO into a state-of-the-art baselines, it automates TVP, NBT, Nomad, and Clyde by reducing the unnecessary page promotion and achieve 85%, 20%, 25%, and 18% performance improvements, respectively. To summarize, we argue that hotness is not enough to describe performance. And then we define AOL as a normal metric to describe MLP impact on slowdown. We further apply AOL on memory allocation and also use it for regulating page migration. Please refer to our paper for more details, such as evaluation on workloads and evaluation under the memory bandwidth contentions. The code will be released soon. And thank you for listening, and happy to take any questions.